So, while we get ready, our next speaker is Dirk Koch. He is an FPGA specialist with research post at Erlangen, Oslo, Manchester, and now he is in Heidelberg. He's professor in Heidelberg. He is the leader of the fabulous eFPGA framework for runtime reconfigurable system deployed in over 10 ASICs projects, and is author of more than 100 publications on the topic, including books like Partial Reconfiguration on FPGAs and FPGAs for software programmers. He will talk about these nice, fabulous eFPGAs.
Yes.
What is yours?
Thanks. Hello. My machine just crashed a second ago, so it was just coming up for the talk, thanks to Microsoft. Yes, first 2 slides is a little bit what my group is doing. So, well, as you see from the word cloud, we are FPGA guys. We work a lot on FPGA CAD tools, mostly for partial reconfiguration. We work on reliability aspects. So if you have a single event upset and you want to know what the flip bit may eventually do to your circuit, for a lot of Xilinx FPGAs, we can tell you. We look in various kinds of applications, database acceleration, data analytics. One of our fun applications is sorting. We can do merge sorting on 2,000 streams in one run at 20 gigabytes per second. We can sort 35,000 numbers in 200 clock cycles, which is a pretty cool one. The red one is what I will talk mostly about today. I have 2 slides on hardware security and a little bit RISC-V work that we do because it's fun, but only 1 slide. Everybody tries to minimize power on a chip. We ask the question the other way around. How much power can you possibly burn? Yeah, and why is this eventually relevant? Well, if you are Amazon Web Services and everybody can go on your equipment, can somebody fry your equipment, damage it, right? And we currently have a hotspot design that can generate in a single Xilinx CRB, which is 8 lookup tables, a little bit over 100 milliwatts power dissipation. How do we do this? We take a 6 gigahertz ring oscillator, fan out on all wires, and if you do this cleverly, it gets you heat. And the chip has 1.2 million lookup tables, so if you take this by 8, multiply this by 100 milliwatts, that's north of 15 kilowatts. If you then use your DSP blocks and block RAMs in addition, you may approach something like 20 kilowatts. It is possible to damage a chip, but we want to do this in a situation that you may have in a data center. So we took a 40-watt hotspot for a week with this power density. Yeah, so it's basically on the tip of a needle, and the bloody chip survived. But we measured that some wires had aged, a few wires have aged by 40%. So, yes. We also look into things like hardware trojans, like you give us a bit stream and it says AES, and we may massage that bit stream for you eventually, those kinds of games. We look into CPU design, software processors. It's early morning, so it's good to do a little bit exercise. Who of you have done a CPU, softcore CPU on an FPGA? Okay, come on, there must be some more. Okay, how many, hold on, leave your arm up, we are not done, it's exercise time, okay. How many of you achieve 50 megahertz and above? Keep your arm up. 100 megahertz, 200 megahertz, 300 megahertz. 300, anybody up? Okay, we got 737 on a MIPS 32 standard integerizer. Yeah, and the trick there is it's incredibly deeply pipelined, and we run as many threads as we have pipeline stages. It's actually super cheap. You get different variants of it from 500 to 700 lookup tables, and that gives you more than 1 RISC-V MIPS per lookup table. Okay. We had the upscale version with 1024 cores, 16,000 threads running at 500 megahertz with PCI Express integration and so forth. But that's not the topic of today. Today it's about embedded FPGAs. Yeah, why doing that? Well, configurability is expensive. Any form of programmability comes at a cost. If you have a CPU, you have 100 instructions, but you fire only one each cycle, right? And if you buy an FPGA, you think you buy lookup tables, right? But what you pay for is the routing. Yeah, the routing is the elephant in the room, is something like 80% of the die area you pay, your transistors, yeah? Think of what your lookup table is. It's fundamentally a large multiplexer, and then think of how many switch matrix multiplexers you need to make this multiplexer work, the lookup table. Yeah? Also, it's much slower than ASICs. It draws more power. Yeah, but somehow we will not get away of FPGAs because there are parts in our system that need the flexibility. So what can we do about it? Well, we just configure or make the stuff reconfigurable that actually needs it. Meaning, if you have a memory control in your system, make it hardened if you can, right? If you need a CPU, make it hardened. Yeah, if it's, let's say, a trigger logic for some, let's say, fancy analog digital converter, maybe that's worth to do in soft logic, yeah? Also, making chips gets to some extent cheaper. I have to say to some extent. If you are not going for the Apple high-end 5 nanometer things and below, if you go, for example, for 130 nanometers, entire mask set is something like 150,000. Yes, it's still money, but it's like what an engineer costs in a year. Yeah? And if you go to 28 nanometers, it's round about $1 million for the mask set. Anyway, so if we do this and we want to build an ASIC with an embedded FPGA, we want to customize it so that the FPGA fits perfect to the application requirement we have in mind. Yeah, and to do this, we need some framework, and we built this fabulous framework. What it does is basically solve 3 parts, here highlighted with 3 boxes coming up. The first one is that you specify your fabric, so you can say, I want so many lookup tables, so many DSPs, so many block RAMs, or you want to throw in your own primitives. Let's say you have a fancy idea of, let's say, Flopoco support or tensor arithmetic for machine learning or something. You can put this all in, and this is in the specification phase. And then we generate RTL code and physical constraints to produce a fabric at the end of the day, and that results in basically the compilation flow to produce an ASIC, right? And on the right-hand side, we generate a model for an open source place and route toolchain. It's based on Joseph and NextPNR. Luckily, I don't have to talk about this because that's Nina's topic later today, yeah? And in this framework, because it still comes with a certain amount of complexity, we take advantage of a large amount of open source projects because they can do the job better than we do. Yeah, and as I said, Joseph, but we also use like Apen Lane eventually for the ASIC part. We did a little bit VPR for doing place and route, but we gave up on that one. Open RAM, for example, the memory macros that you see here for the block RAMs, also they are open source. Okay, yeah, what does it offer? Well, it's a fully integrated open source framework. We aim at pretty good quality of results in terms of area and performance. It's entirely free under permissive license, so you can do with this what you want. If you provide custom cells, you can do so. Custom cells, an FPGA requires an awful amount of multiplexers. And the specific thing in the switch matrix multiplexers on an FPGA is they only switch during configuration, but they don't switch if the user module is running. And that allows us to eventually do the multiplexers a little bit cheaper. Yeah, so we do dedicated customized multiplexers eventually. We also did custom SRAM cells. And if you provide this, you can throw this into the tool and it can take advantage of this one. If you don't, well, we fall back to standard cells. We support partial reconfiguration. It's pretty easy to use. And if you want to customize it, you have full control over everything. It's pretty versatile. We support different tool flows for the ASIC part. Yeah, like I mentioned OpenLane, which is an open source ASIC toolchain, but also the usual industry suspects. Yeah, and on the bitstream side, I mentioned already Joseph. Actually, the VPR support we did in the very first version, but we gave up on that one as NextPNR was just very convenient to use. Yes. Okay. Well, FPGA, you all know, probably if you played with Xilinx Altera, it's basically designed of tiles. You have logic tiles with lookup tables. You may have distributed memory tiles. This would be the slice M's in Xilinx. And maybe you have sometimes tiles that are a little bit bigger, but they embed somehow in a regular tile grid. Yeah, and our fabric is done basically the same way. Yeah, and the way how this is all integrated is that basically usually the lookup table, because that's the most prominent tile, is the one we optimize first, and that defines kind of the height for all the other tiles, right? And even if you have a DSP block, it will be an integer multiple of this basic height. You get the idea. And then you do resource columns in order to adjust the width according to the specific resource requirements you have. But you don't have to worry about this. If you want to specify such a fabric, you can use the world's most advanced engineering tool, which is, well, a spreadsheet program, Excel, whatever. Yeah, and you can just define your individual tiles, and that's all you have to do to specify a chip. I can show you a demo later in the coffee break. I have this on my laptop. The bloody thing just crashed, so I had a virtual machine running, but I will fire this up again, hopefully. Yeah, and if you have this input, we can compile already an FPGA for you, taking our default tiles. Yeah, and don't get confused with this busy slide. The only thing what it shows is that the tiles are designed in a way that they can be stitched together like Lego bricks. And like you have the knobs on a Lego brick, we have wires, and the output wire on one border is directly the input wire of the adjacent border. This is almost what it shows, and then you have the different resource columns like lookup tables, DSPs, and let's say I/O or something, and they will be designed that they I/O pins align perfectly to each other so that we can stitch a fabric. Yeah? But we take care about the physical constraint generation. Yeah, I was talking about a tile. A tile is a basic concept in Fabulous. It always provides a central switch matrix in it, yeah, with wires to all north, east, south, west borders. And we have something like jump wires. This is something useful for describing hierarchies or whatever. Yeah, then we have what we just call these primitives or sometimes basic elements. This would be your lookup table, could be a slice, could be a multiplier. Like that's basically the stuff that does the actual functionality. Yeah, and we provide you the configuration storage. Yeah, and I will not drive you through the green things, but this is like how we define how many wires you have in north, east, south, west direction. Yeah, you can say like what offset the wires get. Like how far do they route? Is it a wire that goes next tile or the second next tile or whatever? Yeah, you can say how many of those wires you have. And if you want to get in your own primitive, you can just program it with some interface and you just instantiate it and we wire it up for you into the fabric. You even can use parameters inside, and the parameters will be then translated later into configuration bits that we also pass through. Then if you generate the fabric, it generates RTL code that gets empty constraints that goes into the ASIC tool flow, but we also generate you a simulation model, we generate you a graphical editor. So what you see here will be built for your specific fabric. Yeah, so this model that you see is generated, and then we have, as default, you get a blinky counter that we run on your fabric, and this is like how you see, like, it's a little bit bad contrast, but you see this red wires, that is actually showing a circuit that is implemented on the fabric. You get roughly an idea. Yeah? If you played with Xilinx or Altera, you may have seen similar things. Okay. I show you a few chips that we did with that one. This one was the first larger one. The display is not the most beautiful one, but you see a little bit, this is running from that FPGA. The FPGA is this tiny thing here, Yeah, you will not see it from the back. I will have it in the coffee break later. Yeah, so the bitmap that you see, the street, is stored in an internal block RAM, or we have 8 block RAMs in total, a kilobyte each. You can configure them in 8, 16, 32 bits. You see the, oops, it's a little fragile. You see like the taller blocks here, they are 8 by 8-bit multipliers with a 20-bit accumulator. That one there is a little bit difficult to see. That's a distributed memory tile. It's basically 4-bit wide, 32 entries deep, and we have one write port to read port. This is what you need to implement a CPU. And why have we put this in? Well, what's the most useless thing you can put on an embedded FPGA? That's actually a softcore CPU. Yeah, if you do an ASIC, right, and you need a CPU, you would not put an FPGA on and then put it in the soft logic. But everybody asks me about stuff that I put on my FPGA. The first question I get is, have you done this or that RISC-V core? Yeah, and it's a little bit like kids, if they cry, they get their sweets eventually. So in order to support softcore CPUs, we put distributed memory in. Yeah, and that was the demo you saw already. This is an open everything FPGA. So you can go on the Git repository, download it, and you can investigate it all the way up to down to the transistor geometry. It's all entirely open. Yeah, this is a fun one. This is using RRAM technology to build a non-volatile FPGA. So traditionally we use latches or SRAM cells, but we also can do non-volatile chips. This is still experimental. This is also still not published, but you get an idea. Yeah. Then we did, you can build weird aspect ratios. So what you see here is like an inverse T-shaped fabric. And in the top corners here, there are 2 IBEX RISC-V cores that use the FPGA as a custom instruction set extension. So how does it work? This is basically the standard picture of an IBEX core. We have somewhere our decoder, instruction decoder. We have a registerfy, ILU, and eventually multiplier. And the interesting part is that we just take the 2 operands, A and B, and route this into the fabric into different slots, right? And then we can multiplex the result from different slots back into the CPU. And again, how do we customize this? Well, by having the routing for the instruction for the operators is already baked into the chip. And this is a fun one because your CPU instruction set is currently blowing up, and because of legacy, you can only add instructions, and over time, your instruction set architecture looks a little bit like that, and try to slice a bread with a super fancy Swiss Army knife. We have other people using fabulous chips. This was done by Stanford University. This was done by TU Graz. This is a RISC-V with a fabulous fabric. New York University, Bristol, Berkeley, Fudan, they all did successful working chips with fabulous. Yes, next steps. We still have to do work a little bit on getting a proper timing model. We are almost done. On the physical constraint, there are a few more things we want to polish, more optimizations. We are currently working on a global foundry 22 nanometer. Hopefully by the end of the year, we have 16 nanometer TMSC FinFET and doing other things. Yes, I have this board also with me. We are working on something like for educational platform, a RISC-V with embedded FPGA, something like the poor people's version of the Zynx chip. And this will get also like a RISC-V and round about 1,000 lookup times. If you want to know more, go on the website. Documentation is all out. And we run a summer school. If you have done ASICs before a little bit, have some basics, join us in August on a summer school. We did this already 2 times before, each time with a chip tape out. And this was one of those where different participants in a hackathon made a chip. That's all I have to say, and my time is currently gone. And yeah, are there any questions? Thank you.
Thank you. So, thank you very much for a very enthusiastic presentation. Do we have any question from the room? Oh, up there.
Hi. From my understanding, this is quite the same that Acronix is offering. Did you compare your results to them of a commercial supplier?
So Acronix plays a card a little bit differently. They are much higher performance, but they also don't allow you to customize your fabric unless you put an awful amount of money in. There are plenty of other ones, for example, QuickLogic. QuickLogic is an interesting one. They have a paper published where they put all details in, and we know that we can beat them in basically any aspect. Yeah, it still needs a little bit more engineering to make a product out of that one, do a little bit more testing. But there is under the hood, I haven't talked about this because of time, we run an awful amount of optimizations to get the logic density pretty high. So we get, for people that did ASICs before, we get 80 to 90% core density, which is basically as good as it can get.
Thank you very much for a very nice presentation. I have a question about the reliability. So do you have any extensions to the Fabulous project that would enable increasing the reliability of the core, for example, by mitigating single event upsets or this type of things?
So we have various thoughts on that one. So the reason why we didn't own SRAM cell was you want to do scrubbing, and this means also eventually you want to read back, compress it into a checksum to see if something flipped. That's on the horizon, and to do this, you fundamentally need an SRAM cell, and the SRAM cell we have to design on our own, because this is actually a tricky one, because if you read an SRAM cell back, it may create a voltage drop for some time. But if this SRAM cell controls your user logic, you don't want any disturbance if you read back and so forth. So you have to take care on that one. There's a fun one specifically for the older FPGAs. If you have a single event upset and it strikes your chip, you have something like a radius of 5 to 10 micrometers where you can expect disturbance. So it's more than a single flop that can switch. Yeah, and if you take this chip, this was done in 130 nanometers, a CLB tile is round about 200 by 200 micrometers. I can put in some spatial redundancy in a way that I keep the redundant parts far away from each other, or my 10 micrometer far away, and so forth. And we have this on our agenda. We'll do this eventually if time, yeah, but there's a person working on that.
Everyone is still thinking about the amazing wheel? Oh no.
On the similar topic, is there any thought on the radiation hardness, like triplet redundancy for the fab design in your case?
Yes, so what I just said goes a little bit into this direction. There are different ways how you can play the redundancy game. You could say you don't care about it at all and you just triplicate your modules itself. Yeah, and in a system you have usually different levels of criticality. So not everything needs to be super duper reliable. Some parts have to be, but some parts don't. We think, for example, putting eventually 9 lookup tables in a CLB, so that you may do 3 that are already redundant, and the lookup table itself comes already with a voter logic and so forth. Yeah, it depends a little bit on specific system requirements and your criticality that you have in your system. But yes, we play or think of doing such games. But if you do this, this is what I mentioned before, you have to keep in mind really the physical aspect that things are spatially separated from each other, so that a strike is not impacting your multiple redundant units. Yes.
Thank you.
I don't see any other raised hands, so I have a few questions myself. Okay, so one thing that came up quite recently was to integrate the FPGAs inside ASICs doing, for example, readout of hybrid pixel detectors and stuff like that. Would you be able to like create a core for an FPGA with your tools and then integrate it in an ASIC doing other specific things?
Well, to some extent, this is what we do. There is actually a project that's done in Manchester still using more CGAs. And if you have, for example, wider vectors that you route, you may not want to do just everything at bit level granularity. We have support for that one. This is not exactly what Xilinx is doing with their AI engines, but you could basically have something like DSP blocks or custom blocks that could even have wider data paths, and this gets then also integrated, and you get the tool chain to map applications to this, route this, and so forth, if this answers the question.
Yeah, I was thinking more like having some like of analog part.
Okay.
Plus then the data get digitized and get sent to the FPGA.
So usually the analog part you want to put outside of the fabric for various reasons.
Separated but close by, let's say.
Yes, but we call this attached peripherals. So in that chip here, you can't see this there are somewhere, I think that is a digital analog converter, and it's basically attached to the fabric. And the you can wire out configuration bits. So if you have an analog digital converter and it needs some control bits to control, I don't know how many bits you want to have or how fast it should be if you want to trade that one, this can be controlled directly by the fabric. We did this one. And that thing here, this part in this corner, is actually a digital analog converter attached directly to the fabric.
Okay, and also in this direction, so you can somehow tailor the FPGA to your algorithm, let's say? Not really. So is there a way to, like, what's the proper way to do this? And how much of the algorithm should I write before in order to understand like what I need? And
what I suggest people is don't think about the FPGA in the first place, just do your algorithm, and then you basically see like how does it fit on a standard FPGA, and then you know, for example, how big should your DSP blocks are. This is just a generic parameter. So do you want 8 bits or maybe whatever bit width you come up with, and then you can adjust the fabric according to that one. Yeah.
And what's the level of the configurability of the single blocks? Because you showed this amazing spreadsheet, but I guess that is only the floor planning of the blocks, let's say.
So you can throw in your own primitives. That's super simple. That's directly supported. If you put in arbitrary, for example, arithmetic or memory blocks, this needs a little bit massaging of the Joseph tool chain to get to tell the tool, for example, what's the bit size. Yeah, so even if you have, let's say, 8-bit multipliers, you can still do 22 by 30, whatever, and the compiler will puzzle this together out of multiple smaller ones. But you have to tell the tool what's the baseline multiplier, and the same applies to memory too. So there's for those things already something there. And if you have specialized blocks like DSPs, think of Xilinx DSPs or the Altera ones. They are very complex. They have like floating point units, but then later you would instantiate them and parameterize them, yeah? Which is fundamentally what your visit is doing if you call the core visit. Yes?
Okay, thanks. Are there any other questions, maybe remote? Okay. If not, thanks for the presentation, and thanks for the nice demonstration.